So there is a certain quantity that can be ascribed to any configuration. So for any point in the n simplex, which is called the entropy, or alternatively, it can be seen as the expected surprise of a configuration. And the question would be, how do we obtain a category from this data? Well, what we do is we take all of the pairs of configurations such that the entropy change is greater or equal to 0, which is kind of in accord with second law of thermodynamics. And each pair Q comma P is interpreted as the transition going from P to Q. And you can immediately see like this, like C is now the set of morphisms of this this category. This is the set of objects, right? The n simplex. And you can immediately see, these two guys have a certain topological structure, and so you can start asking questions. Do they have a smooth structure? It turns out they don't yet. We have to remove a bunch of points from the n simplex so that we actually obtain a smooth category. But let's not go into these details right now. So let us discuss notation before continuing. So we are going to be using the following notation. So our category will be denoted by C double arrow X. X is the set of objects and C is the set of morphisms. And our small categories will be, so all of our categories will be small. So the set of states, the set of morphisms, these are always sets. Any small category comes equipped with a source and target map, which is to say the source map. Takes as input an arrow from C and spits out an object, which is just the domain of the arrow. And similarly for the target map, it spits out the codomain of the arrow. Okay, but apart from that, we also have the composition and the unit maps. So the composition map, what it does is basically takes two morphisms and composes them. This is something that's like inherent to the category, that this is possible to do in a category, right? And so what is this C2, this set of composable arrows? Well, it's just pairs of arrows such that the source of the first one is the target of the second, right? And in this way, we obtain, like M is suggested because it's kind of reminiscent of multiplication, right? And on the other hand, we also have the unit map, which basically for any object, it gives you the identity morphism on that object, right? Yeah, and of course, I'm not giving you all of the details regarding the category. One should keep in mind the associativity axiom, for example, if I multiply G with the appropriate unit, I again get G, where G is from a morphism, right? So this is the first thing that regards notation, and the second thing is that we are going to be denoting so the source fibers with C X X below, C underscore X. We are going to be denoting the target fibers in a similar manner, but now the index is going to be like on top instead of below, and the set of all arrows from X to Y, which is to mathematicians also known as the home set from X to Y, will be denoted as CXY. And also, last thing that regards notation, we are going to be denoting the left multiplication. I call it left multiplication because it's really just the left multiplication when it comes to groups, for example. But in fact, it's pre-composition and post-composition maps. And you may be wondering why I'm denoting, like, y are the domain and codomain of, say, precomposition given by, so by these two target fibers. And it's kind of obvious, right? Because I have a G, right? Well, what can I compose it with? Well, with something that has target of, yeah, that has target equal to source, source of G, right? So, and this literally means I can only act by with G from the left on target fiber CSG. And what does it what does it spit out in this product? Well, of course, it spits out something that has target equal to target of G, right? So this is as far as our notation goes. It may seem a little bit non-standard to some. All right, so let us define what a Lie category is. So it's a category, a small one. So the classes of states or of objects and morphisms are sets, and not only they are sets, they are also smooth manifolds. Okay, the very next thing that we are going to require is that the source and target map are smooth submergence. So this will become clear why we are requiring this in just a second. And the last kind of, let's say, natural requirement would be that the composition map and the unit map are smooth maps were internal to the category of smooth manifolds, right? So before kind of shedding some light as to why we are having this second requirement here, let us only mention that we are going to always require the object manifold X to have no boundary, but allow the set of all states to be a manifold. The set of all morphisms, sorry, to be a manifold with boundary. And if it does, then we are going to also impose that the restriction of the source and target map to the boundary are submersions. Okay, and there's some nomenclature here, we're going to call this the regular boundary condition. Okay, but now, because differential geometers rarely ever care about boundaries, we are going to, for a moment, assume that our set of all morphisms has no boundary. So because of the assumption that S and T are smooth submersions, we immediately get, of course, that the source and target fiber are smooth submanifolds, right, in the set of all the space of all morphisms. And this is by virtue of implicit map theorem. Secondly, why can we even require that multiplication is smooth? So because S and T are smooth submersions, we can view this set of all composable morphisms as the pre-image of the diagonal. This is just the diagonal inside X times X. Okay, so we can actually view the set of all composable pairs of morphisms as a smooth submanifold of the product C times C. Okay, this is by virtue of transversality theorem now. So, as I've said, now the requirement of composition being smooth is now sensible. Okay, moreover, the pre-composition and post-composition map automatically become smooth maps because they're just compositions of smooth maps, and in this way we obtain a covariant functor from C to the category of smooth manifolds given by on objects by X gets mapped to the fiber, the target fiber over X, and G gets mapped to left multiplication. So, of course, if we were just dealing with a normal category, with a small category, this diff here would just be set, right? Now we can kind of change that category of all sets we can exchange it with the category of smooth manifolds, right? So we get a covariant functor and a contravariant functor here. And moreover, the units can automatically be seen as as the objects of our category, right? We have the following smooth map, the unit map, which goes from the set of all states to our set of all morphisms. And because this is a section of a smooth submersion, it's an like the unit map is an injective immersion, and the homomorphism onto its image because it has a continuous inverse, right? So we can actually see objects of our Lie category as if they were embedded in the as units, right? Okay, so regarding the case where when we have a boundary, so the regular boundary condition ensures that all of these properties still hold, because yeah, this is essentially this is something that's called to be neatly embedded, right? You may have observed or seen this, but if you have never dealt with manifolds with boundaries and implicit map theorems before, then maybe you haven't. So first of all, what I'm saying just now is that because of the regular boundary assumption, well, the boundary of our source and target fibers is just the same source and target fibers, but intersected with the boundary. Okay? And not only that, this C2, this set of all composable pairs of morphisms, remains a smooth manifold with corners because the transversality theorems for manifolds with corners were developed in the 90s, and we can kind of rest assured that everything still holds true. So my question for the audience is whether you can guess what the corners of this guy are.
Can I first ask, if you take a disk and then map it to a sphere, this one is not regular in a sense.
And this one is not what?
Regular in a sense. I mean, that's a disk is a manifold.
If I map, what map do you have in mind?
I mean, you just contract the. I mean, so that's like what is it kind of.
You puncture the disk first and then contract it to the.
No, I don't. I mean, I just take a closed disk and map the boundary north of the sphere. But that's not regular in our sense.
Yeah, I'm not sure I understand.
Okay, take a disk and just make.
Okay. Yeah.
Okay, so I mean, you can make it smoothly, but it will not be. I mean, actually, I don't recall the definition that you had on some of the previous slides.
Okay, maybe I moved that bit too fast. We can go back.
Okay. Oh yeah, that is
so you do need a certain
yes.
You do need a certain sense of composing stuff here, right? So if you are trying to define a certain Lie category at this very moment, you're going to have to tell me what the composition is.
Okay, so in order to be regular, I mean, C and X are usually not on the same dimension, but
yeah,
they could be.
They could be.
Anyway, if they are not on the same, I mean, if they are on the same dimension, then it cannot be regular on the boundary.
Yeah, in that case, the manifold of morphisms would necessarily not have a boundary. And moreover, the source and target fibers would actually be discrete. Right?
Mm-hmm.
So.
Okay, can you give us an example of a regular? I mean,
I will come to a lot of examples. Like all of these dots here are basically examples. So so I want to I want to actually continue with examples just now. Okay, so but before continuing, maybe let us just guess what the corners are here. So basically, what we have is we have the set of all composable morphisms lying inside the product, right? This is a manifold with corners because C has a boundary, right? So the set of corners in here is precisely, let me write corners of C2 is just the set of all pairs from the corners of here, which are composable. Okay. So this is sometimes called a totally neat submanifold. The nomenclature is silly. Okay, so let us continue with examples, which are surely necessary in order to kind of shed some light to this kind of abstract definition of a Lie category. So first of all, if we have the set of all states or the set of all objects a singleton, we just get a Lie monoid, right? Because like every two morphisms are composable, right? And so we can equivalently we can restate the definition of a Lie monoid. We can just say, it's a smooth manifold, or it's a monoid together with a structure of a smooth manifold, possibly with a boundary, such that the multiplication of the in the monoid is smooth, right? So turning to more specific examples, of course, we have immediately Lie groups, which we are very much acquainted to already, right? The very next example would be, for example, the half space HN for addition, for just the restriction of the ordinary addition on Rn, or we could have the closed half ray for multiplication. Moving on, we can consider matrices for multiplication, or more generally endomorphisms of a finite dimensional vector space V.
Once again, what is HN?
HN is, okay, maybe I can write it down. It's just the half space, closed half space.
Okay, because I mean, Q line, we are using the same H for.
Yeah, okay. These H and these H are not the same H's. Yeah, so I'm sorry about that.
Is this an open interval from 0 to infinity?
So it can be like, if it's an open interval from 0 to infinity, then it's a group, right? For multiplication.
Monoids also have units.
Yeah, but the unit here for multiplication is 1.
What is 1 times 0?
0.
So it's not open.
Yeah, 0 is an absorbing element.
Yeah,
mathematicians are very used to talking about groups, like, like, what about monoids? Well, of course, we just remove the invertibility assumption, right? But and 0 isn't invertible in this particular scenario. So yeah. So let us continue with these examples. We can also consider any finite dimensional unital algebra, or we can consider for example, the set of all n times n matrices which have determinant lying between 0 and 1, 0 excluded. Or we can consider, so of course the unit here is just the identity matrix, right? Or we can consider the closed disk for multiplication in the complex plane. Or we can consider this kind of a Hawaii ring stuff, which is not, it's not really a Hawaii ring. So this would have radius 1, this would have radius 1/2, this would have radius 1/4, etc. Right? And if we multiply, I guess, this guy with this guy, we're going to just sum up the angles and end up here, right? Because 1 times 1/2 is 1/2. So there's a plethora of examples that you can come up with. Of course, the assumptions of like the source and target maps here being submersions, or their restrictions to the boundary being submersions, that's vacuously true, because our manifold of objects is 0-dimensional. So we have nothing to, we have nothing to prove. Okay, so this is the first example. The second example is a kind of a trivial one. So you take any smooth manifold, any Lie monoid, okay, and form the following product: x times m times x. And this is going to be our set of all morphisms. And now we have to, of course, tell what the structure maps are. What's the source map? What's the target map, etc. And the source map is just going to be projection onto this vector. Target map is just going to be projection onto this vector. And we also have to tell what the composition of morphisms is. Well, the source and target must coincide. So these two guys have to be the same. And now you have to consider what this product should be. Well, we just multiply G and H and leave out this, right? So this is kind of what a trivial Lie category would be. It's just a kind of a product. And for the case when M is the trivial group, we get the so-called pair groupoid. So basically, in that case, like all of these multiplications here are kind of vacuous, so we can also leave out the E or whatever. All right, and so this is kind of inspired by a certain theory called the theory of Lie groupoids, and we are also going to talk a little bit about them. But before moving on to that, we can actually consider a certain Lie category that comes out of the pair groupoid on R. So the pair groupoid on R is just R times R, okay? And we can now throw half of the arrows away, and basically we can do that because we have the structure of total order on R. And now we can consider, of course, the set of all such pairs, and this is nothing else but the order category on R. So, and this is very simple to visualize now. It's basically just the half space below the diagonal in R2. And so I'm not sure if you can see what's written here. It's the points in here are trying to tell you how to multiply stuff. So if I take any pair, yx, that's, let's say it's here, right? My question would be, what can I multiply it with? So yeah, from the left. So I have yx. I want to like put something here and like make out the multiplication, right? I want to see kind of visually what it is. And of course, I can only multiply it with the thing with anything that is here, right? I just follow a vertical path and bounce off the diagonal, and I can multiply this thing with anything that's on this line, right? And where am I going to end up? Well, here, right? because I have to, you know, erase the y's, if you agree. So this is the way in which like multiplication or composition in the order category works. So this is very easy to visualize, and it's also immediate that this guy is a Lie category, so that it's internal to the category of smooth manifolds.
But so your objects are the lower half plane.
No, those are my arrows, my morphisms. My objects are just R.
Okay.
So my set of objects is just R.
Yeah.
Or alternatively, you can see the objects as the diagonal, right? These would precisely correspond to identity morphisms, right? And so you see why I'm saying we are throwing half of the arrows away, because like if we were to have inversion would literally be reflection over the diagonal, right? And we're kind of throwing half of them away. All right. So next example is kind of illustrative because it's giving us a first example from differential geometry, really. So if we are given a vector bundle with the typical fiber finite dimensional vector space V, we can consider the set of all linear maps between fibers. Okay, so just put all of these linear maps between fibers in a bag and call it like it's a set, obviously, right? It's a disjoint union of vector spaces even, and so we call this guy NE, and this is a category over X with obvious structure maps. Structure maps being target would just be like for this guy, it would just be Y, right? Source would just be X. What's composition? You just compose two linear maps. What's the unit map? Is just the identity map on each fiber. So, and of course, to maybe satisfy briefly the audience, we have to talk about the smoothness of this category, right? And so what these particular maps here are doing is they are defining smooth charts on this guy, right? So, and so you take local trivializations of your vector bundle. How do you obtain the charts on your space of morphisms? Well, you have to keep in mind that you're adding so of course you're going to have in a certain way you're going to have a vector space here consisting of linear maps, right? But now you're also changing the source and target map. So you are kind of introducing new degrees of freedom, right? So, and this is what this UJ and Y do. And so how does, I'm not sure if I should say another word about it, because this particular formula is just here to kind of say this thing plays out. Okay, it's not a particularly difficult or complicated formula to explain, but I'm not sure if I should. So you can believe my word for it. You can kind of believe when I say this is a Lie category, so that we don't have to go into that detail. And the bonus is that this guy, this NE, is moreover enriched over the category of vector spaces. So what does that mean? That merely means that the home sets are vector spaces and the composition is bilinear. Okay, so this is kind of a bonus that we, that was not present until now in the theory of Lie groupoids, which we will encounter very soon. So yeah, and what's the moral of this last example is that Lie categories can be used to describe smooth families of endomorphisms of an abstract structure that's parametrized by the base manifold. So, all right, the very next example would be the example of a bundle of Lie monoids. So this just means we have coinciding source and target maps, which literally means we can only compose within the fiber. Okay, let me give you a very brief example. I have a vector bundle, right? Where can I add stuff? Only in the fiber of my vector bundle, right? This is a very simple example of a bundle of Lie monoids, but that's not the only one. We can also consider the endomorphism bundle, which would just be the same thing as before, as in and E, but now X and Y have to be the same, right? We can just restrict to linear maps over particular fibers, like endomorphisms of a fiber, right? And this is a subcategory of and E. Okay, so there's a bit of a nomenclature here, right? I'm calling this the endomorphism bundle, and it's a subcategory of the endomorphism category, right? And moreover, we can also see the exterior bundle as a bundle of Lie monoids. How? Well, how do we multiply multivectors or pointwise differential forms or whatever you want to call them? Well, we just take their wedge product, right? They remain within the same fiber. And what are the units? Well, they're just ones which come from the underlying field over which this vector bundle is modeled or whatever. So these are bundles of Lie monoids. And note that these two particular examples are kind of misleading. So both of these are locally trivial, but they are not necessarily such. Like in all generality, the only thing that we're requiring is that S and T equal to P. So I mean that S and T coincide. Okay. So, and with these two examples, we also get the bonus from before. We also get that these two guys are enriched over the category of vector spaces. So, and what, for example, I claim is that Lie categories or bundles of Lie monoids that are enriched over the category of vector spaces is something that would rightfully be called a bundle of unital associative algebras. So we have a smooth multiplication and we have a certain kind of linear structure that is changing fiber-wise, right? Okay, and the example that I've been kind of mentioning is the example of a Lie groupoid, which is nothing less than a category, a Lie category where all morphisms are invertible. Okay, so and these guys enjoy a lot of attention from differential geometers. So kind of Lie groupoids are very popular to research nowadays. And let us briefly mention a few examples. So we have the example of a bundle of Lie groups, which is just as before, a bundle of Lie monoids, but now everything is invertible. And I've already mentioned the example, right? Vector bundles for addition. The next example would be the example of a fundamental groupoid of a smooth manifold. So these are just homotopy classes of paths relative to endpoints, right? And we can, how do we invert? Where we just go like in the opposite direction, right? So moreover, generalizing the fundamental groupoid, we have the monodromy groupoid. So whenever we have a foliated manifold, we can say, so take homotopy classes of paths relative to endpoints, which are contained within the leaves of the foliation, right? This is just an improvement of the previous example, nothing nothing special. Then there's the example of a gauge groupoid. So if you're given a principal bundle, you can consider the set of all G equivariant maps between the fibers of a principal bundle, which is kind of imitating what was happening before with the endomorphism bundle of a vector bundle, right? So we are taking kind of the endomorphisms, but only fiber-wise, in a certain way. And for the last one, so symplectic groupoids are really important in Poisson geometry because so what they are Lie groupoids endowed with a kind of a certain structure that's called multiplicative and symplectic at the same time. And these guys correspond kind of to integrated counterparts of Poisson geometry. So these guys are really popular to study within Poisson geometry. All right, let us maybe now focus on reversibility. So let us focus on reversible morphisms of any Lie category. Of course, we can, if we are given a Lie category C, we can consider the set of all invertible morphisms, right? This is a subcategory, and the natural question is this a smooth submanifold? So is it a Lie groupoid? Is it open, right? And in general, it's neither, because we're allowing our category to have a boundary, right? If we just take the disjoint union of the pair groupoid and the order category, what happens is, like, we can invert here, right? And this is a two-dimensional manifold. Here, we cannot invert. The only invertibles are on the diagonal, and this is something one-dimensional. So, kind of, we have a set that would be, consisting of two different dimensions. And of course, you can say, yeah, but this example is not connected, right? Sure, but that's not the issue here. The issue is that we allowed the units to be contained within the interior of our category, of our set of all morphisms, and we allowed them to be contained on the boundary. So, and how do we kind of progress with this? So there's a very simple observation that's kind of, I like to call this units dictate invertibles. Okay, so what this lemma is saying is that in any Lie category, if all of the units lie within the interior, then all of the invertible morphisms are going to lie within the interior as well, right? And if the units lie on the boundary, then all of the invertibles have to lie on the boundary. And this is a very simple thing. It might seem abstract, but in fact, it's really simple. So why is this simple? Let's take an invertible morphism G, right? Because G is invertible, LG, which goes from this source, target fiber to this target fiber. This is a diffeomorphism, right? And what does it do? It maps the unit at S of G, it maps it to G, right? So if the unit is in the interior of this guy, then G must be in the interior as well of this guy, because we have that this is a diffeomorphism because of invertibility of G, right? And so we can do the same kind of thing for the right multiplication, and of course we have to use the fact that so it was on the board before, the boundary of any target fiber is just the target fiber intersected with the boundary, right? So the fact that these guys are neat submanifolds. And this is basically the proof of this lemma, right? So, and what happens in the case of Lie monoids is really simple, right? Because now you have only one unit. Where can it lie? And it can be either in the interior or on the boundary. So this literally means all the invertible elements of a Lie monoid must either be in the interior or in the boundary. Okay, if you agree. And this is, yeah, you can see this in various examples. This guy for multiplication, for example, right? This guy for multiplication, what are its invertible elements?
Except 0.
0. Is it for multiplication then, or is it for addition?
Except 0 for multiplication.
0 is invertible for addition. For addition. For multiplication is the whole interior, right? So in this particular example, the invertible morphisms are either the whole interior or the whole boundary, right? It may seem trivial, but this is kind of a simple example that shows this fact. Okay, so in order to continue talking about invertible morphisms, to come up with the sufficient conditions for the core to be a Lie groupoid, we now require this to hold. We now require that either the units are in the interior or the units are in the boundary, but now it turns out we also have to impose a certain condition, that is that the boundary of the set of all morphisms is a subcategory in itself. So that if you, this literally means if you multiply two things from the boundary, you stay in the boundary, right? That's all. Well, and in this case, we do get that the core is a Lie subgroupoid. It's a Lie groupoid. So, and more precisely, what we get is if the units lie within the interior of our category, then the set of all invertible morphisms is open in our category. So this is the manifold interior. Okay. And if the units lie on the boundary, then the set of all invertible morphisms is going to be open in the boundary, right? It can be open in the whole category because the boundary in itself is a submanifold of codimension 1, and there's no way that the guy is going to be open, right? And so now, if you want to see how this would be proved, I can try to give you the idea. Are you interested? Okay. So basically, before proving this, let me just give a kind of a history about this. So this particular theorem for boundaryless categories, so when the space of morphisms has no boundary, it was proven by Eresman in 1959, I think, or 1958. So at the end of the 50s. It was proven in local coordinates. And so it's kind of messy. When I first saw it, I had to kind of Google Translate from French, and it was messy. I could not see anything because it was in local coordinates. So conceptually, it wasn't really clear. And that was kind of the first step for me when I was researching this stuff. That was basically the first proof that I kind of wanted to translate into modern language of smooth manifolds, like in the invariant way. So
what was Eresman's version? Monoids?
No, he was also talking about Lie categories, but he did not permit C to have a boundary. So the set of morphisms was just a manifold without boundary. And then this guy is automatically satisfied so that the core must be open in the category. So, and basically that's kind of, it goes with the moral in mathematics. So if you have a Banach algebra, then the set of all invertible elements is open, right? For example. So there's this moral that the set of all invertible things kind of constitutes an open subset. The same goes, for example, for invertible matrices, right? It's open within R n times n. Okay, so let us indeed work with this to kind of simplify stuff. There are kind of a few more steps that we should do in order to kind of take care of the boundary, but the gist of the idea is here. So what do? Well, we define the following map. So map that takes a pair of composable morphisms, G, comma, GH. Okay, and what's this here? Probably have to define this. This is the set of all GH such that T of G is T of H. Okay, so of course the target of this guy is the target of this guy because we have G on the left, right? And now, what's the first step in the proof is that the theta G minus 1. So this is the differential of this smooth map at the point G minus 1. Of course, these two guys are composable, right? This is an isomorphism, provided G is invertible. Of course, otherwise we cannot form this G minus 1, right? Okay, so by virtue of altogether inverse map theorem, right? This guy is a local diffeomorphism at point G minus 1. Okay, so there exists an open neighborhood of G minus 1 and an open neighborhood of, so when we multiply these two, what we get? G and one target of G, right? These two neighborhoods such that theta restricted to U to B is a diffeom, right? Inverse map theorem. All right, so next step, what do? We observe that there's a certain map, there's a certain embedding, which I am going to now call lambda for the lack of a better symbol. It goes from C into this fibered product. And what does it do? Well, we can't do much else than this, right? So, and this is again a smooth map. Not only that, it's an embedding. Okay. So now the only thing that's left to do is to observe really that this guy is it's an open set, of course. This guy is continuous, this guy is open. That lambda to the power of -1 of B is a neighborhood of my invertible element G, such that all the elements inside here have right inverses. Okay? So in this way, we obtain a neighborhood of G, of an invertible element G, that such that all elements here, all the morphisms inside here, have a right inverse, which would literally mean there exists, like these are all such G's such that there exists an H such that GH is 1 at appropriate point, right? And of course, we can do the very same thing for I'm not sure how to say this, like for left invertible morphisms, for left invertible neighborhood, right? Because you can take this guy and you can map it to C and like now just exchange T by S, put GH here and H here, right? And you obtain a neighborhood that is left invertible in the very same manner. Now intersecting these two, what do we get? We get like a neighborhood such that all of the elements have the left and the right inverses, right? And now because they have the left and the right inverses, they have to be the unique invertible morphism that inverts the morphism in question. So this is kind of the trick. Basically, the gist of the proof is to use the inverse map theorem in a kind of in a clever way. Okay. So, and this is for empty boundary, of course. Yeah, maybe I should say that. Yeah.
Just one question. I mean, this set B, it's open in the product, right?
In the fiber product.
Yes. So I mean, it contains some box neighborhood around G identity.
Well, it's the fibered product intersected with the box neighborhood. Yeah.
Okay. And that's, I mean, the first component is already an open neighborhood of G.
Yeah, but it's not that simple because you have to watch what you can multiply now, right? So there's this kind of you know, something that's constantly above your head is I can't multiply just any two things, right? As I could, for example, with Lie monoids. So that's where it gets a bit complicated. Okay, let's continue. So the first corollary of this thing is that this guy, this G, right, is a functor. So how does it act on what does it act? Okay, first of all, we have the category of all Lie categories with a normal boundary, and we have like what are morphisms between them. They are smooth functors, right? It's kind of an analog of a morphism of Lie groups, right? Instead of smooth homomorphism, I say smooth functor. Okay. And because they must map invertible, any functor must map invertible elements to invertible elements. So basically what I'm saying is it maps the core to the core. We can define this G on any functor just by taking the restriction to this guy, right? And because this is a smooth manifold now, because we're restricting to the Lie categories with a normal boundary, so this is going to be a smooth map, right? And so in this way, we obtain a functor from the category of Lie categories with a normal boundary to the category of all Lie groupoids without boundary. Okay, so this is kind of just a very simple corollary of this fact. All right. Now for the next thing, what I want to discuss is infinitesimal structure of any Lie category. So of course you should be like you should see here, we have the notion of a Lie group, right? We have the notion of a Lie algebra. To any Lie group, we can associate a Lie algebra, right? And now, if you kind of have a, I'm probably assuming too much, but like if your like brain is saying a smooth structure, and I have some compositions here, and I have or multiplications, you know, you can kind of see it. Okay, the proof is going to the proof of the construction of Lie algebras is kind of going to carry through to this setting of Lie categories. Okay, so and before doing this construction, let us first define what a Lie algebra is. Okay, it's the analog of a Lie algebra where we have so not only one object but many objects, right? So it's basically a vector bundle such that we have a Lie bracket on its sections, and it comes also equipped with a morphism of vector bundles from this vector bundle of ours that we are just talking about to the tangent bundle of the base manifold. It's called the anchor of our Lie algebroid. And we assume that these two guys are kind of compatible in a sense. So what this means is there is a certain kind of Leibniz rule that holds. Okay, so basically what this definition is saying is a Lie algebroid is kind of a vector bundle equipped with a Lie bracket. Okay, of course, if you're talking about tangent bundles, these guys always come with Lie brackets, right? But not every vector bundle comes with a Lie bracket. And this is our way of kind of imposing the Lie bracket onto it. Okay. So this is an abstract definition. Now let us carry this discussion to the construction of a Lie algebra of a Lie algebroid of a Lie category. So
you can just return to the previous slide.
Yes.
So this anchor is something that is given. It's not.
It's given. It's given, but for Lie categories, there's going to be a natural candidate. What it's going to be, like, what I'm saying is there is going to be a Lie algebra that we can associate to a Lie category. Okay. Yeah, both the bracket and the anchor is like, axiomatically given, right? All right, so how do we generalize the construction of a Lie algebra of a Lie group? So you have to remember what how the construction took place, right? You were talking about left invariant vector fields on a Lie group. So, and it was defined by this particular formula here, right? And of course, G and H were always something composable. You could always multiply any two elements of your Lie group. But now, again, there's the obstruction that not every two morphisms are composable. Of course, you're in a category, right? So you can only expect this particular thing for composable morphisms, right? You can impose this condition for composable morphisms. But in order to say that something like this would even hold for a vector field, you have to assume that X is tangent to T fibers. Why? Well, it's pretty simple again. It's because left translation is only defined on T fibers, right? Left translation by G is only defined on T fibers. So, of course, this guy has to be tangent to target fibers, otherwise, like this second line does not make sense. If you agree.
I just suggest not to use this thing as a pointer.
Ah, yeah. All right. So in the very same way that we prove this lemma for Lie algebras of Lie groups, we can prove this guy for left invariant vector field. So what this lemma now is saying is that the vector space of all left invariant vector fields is closed under the Lie bracket, which means that if I take the Lie bracket, so the very Lie bracket on TC, right? These are vector fields. I have a natural Lie bracket here, right? If I take two left invariant vector fields and form their Lie bracket, it's again going to be left invariant. This is what this word here is saying, right? It's closed under the Lie bracket. Okay. And moreover, it's canonically isomorphic to the vector space of sections of the following vector bundles. So this now is a very complicated way to say a very simple thing. Like remember, from the theory of Lie groups, what do you have? You have left invariant vector fields, and it's the same as the tangent space of the identity, right? Okay, now what this guy is doing is just restricting the target fibers, the kernel of DT, to the units. Okay, so basically this is a multi-object analog of the construction that we've all seen for left invariant vector fields on Lie groups, right? And yeah, the isomorphism between this set of all left invariant vector fields and the vector space of sections of this guy is given precisely by restricting to the units. Okay, so now finally let us define what a Lie algebroid of a Lie category is. Well, of course, we have two possibilities of how to define the Lie algebroid, right? We can take either left invariant vector fields or right invariant vector fields. And if you remember from the theory of Lie groups, we had a certain isomorphism, canonical isomorphism between them that was given by inversion, right? But now in Lie categories, there is no inversion, right? In general, we don't have inversion. So these two guys, they might be different, right? For certain ill-behaved Lie categories. So what we do is we define the left Lie algebroid of a Lie category as the vector bundle. So ALC. So let me write it once more. So it's here on the board. AL of C. This is just sorry. This is just the disjoint union kernel DT1S. Sorry, 1X. Okay. Basically, I'm just restricting the kernel of the differential of the target map to my units, which are embedded, right? These are just objects embedded in the in my category, as stated before. Okay, so I have this vector bundle. What's the Lie bracket? Well, it's just going to be the bracket as induced by this isomorphism of these two vector spaces. And what's going to be the anchor map? Well, we are in the kernel of DT. We also have another map, structure map, that's possible to use, and it's the source map, right? So we just use the differential of the source map in order to obtain the anchor map. Okay, and this turns out to satisfy the axioms of Lie algebroid. This is like kind of saying there's a natural candidate for describing infinitesimal structure of a Lie category, but there's a kind of a left one and the right one. Okay, there's kind of an asymmetry here. And in the very same way, we define the right Lie algebroid. So on a Lie groupoid, these two guys are going to be canonically isomorphic, and the isomorphism is going to be induced by the inversion map, as stated for Lie groups, right? And moreover, there's a certain notion of morphism of Lie algebroids. So it has to, in a way, respect the anchors. And so if we are given morphism of Lie categories, it's going to induce a morphism between the respective either left or right Lie algebroids. And this is precisely the same thing as happened in the case of Lie groups and Lie algebras, right? If you have a homomorphism of Lie groups, it induces a homomorphism of respective Lie algebras, right? So, in fact, what happens in the end is that AL and AR are going to be functors taking Lie categories to Lie algebroids. Yeah. So the question is, are these, for example, I have a Lie category with a normal boundary. I have a Lie groupoid that is constituted by the core. I can take the algebroid of either the category or the algebroid of the core, either left or right one, right? And the question is, are these guys going to be the same? Are these algebroids going to coincide? And now, because of our previous theorem, whose proof is stated here, if the units of a Lie category are contained in the interior, so now the core is going to be open because of this guy, right? And the left and right algebroids of our Lie category are isomorphic to the Lie algebroid of the core. And this happens because, like, this is, you should keep in mind, this is like infinitesimal data, of course, right? Our core is now open by this theorem in our category, so it doesn't matter like what's going on infinitesimally. These two guys are going to be the same, right? So this is the kind of the first corollary of that really has some depth of the previous theorem. And on the other hand, if we are going to have a normal boundary, but this boundary is going to be a wide subcategory in the sense that it's going to be a subcategory plus it's going to contain all of the units, right? Well, then the Lie algebroid of the core will always fail to be isomorphic to the algebroids of the category, because, like, for the simple reason that the rank of the vector bundle algebroid of the core is one less than the rank of the algebroids of the category. And this is like, this may seem a bit like abstract, but if you start thinking about examples, it's kind of really trivial. So if I take, for example, the monoid that is the commutative monoid upper half space for addition, right? So of course, the tangent space at 0 is just going to be this R2, right? And now you have to take a look at the core. What's the core? So which morphisms, which elements are invertible here? Well, only those that are here, right? So obviously, we are going to get a certain kind of Lie algebra with dimension 1 less than that with the upper half space. Okay, another multi-object example of this particular phenomenon would be the order category. So let's again draw pictures, because like that's what one has to do with this abstract things. So the order category looked like this, right? So this is the diagonal in R2. The only invertible elements are here, right, on the diagonal. So, and how do we talk about the algebraics of these guys? Well, here you can immediately see this is going to be a kind of a not even a trivial category, something that's not even permitted to be, you know, it doesn't even deserve the name of a trivial category, because it's literally just the base groupoid. What that means is that for any object, I only have the identity, right? It's kind of a, yeah, it's a base groupoid. And in this particular case, the source and targets coincide, the anchor is 0. Not only that, like the whole algebroid is actually going to be the 0 vector bundle of I'm talking about the core still, right? Whereas target fibers are these in my Lie category here, in my order category, right? So the vector bundle point-wise is going to look like these vector spaces here, right? So these guys are not obviously not going to be isomorphic, one algebroid and the other. And but we do conjecture one thing. So if we do indeed have a wide subcategory, then so the boundary being a wide subcategory, then the left and right algebroids of our Lie category are still going to be isomorphic, but not canonically. Okay. Before, in the case where we had units lying inside the interior, they were isomorphic because they were both isomorphic to the algebroid of the groupoid, right, of the core. But now, like this isomorphism is not going to come naturally. It's not going to come canonically. Okay.
Just one question. So when you say, so to be wide subcategory,
yeah,
means that the boundary is a subcategory.
It means that the boundary is a subcategory and all of the units lie in the boundary. Right. So it's basically a subcategory that has all of the objects.
So if C is the wide subcategory. I'm not getting, so I mean, what was this? How do you read this? If boundary of C.
If the boundary of C is a wide subcategory of C.
Okay, to me, wide subcategory means it is a subcategory and it contains it.
It contains all of the units, yeah. Yeah, precisely. So seeing that I've already almost run out of time, I'm going to save this last thing that's here, which is not visible, the rank of a morphism, the notion of a rank of a morphism. I'm going to save it for next time, and maybe rather leave space for some questions here, because I'm sure that some of you might have some or not.
Yes, first of all, thank you. And we are not used to clap here, but we usually have questions, and especially from you. And since this is
I have questions, but I will wait for others to.
What?
I have some questions, or I had 2 questions, but you have already answered one of them, and I still have one.
Okay.
You didn't ask any so far, so please go ahead.
Okay, so we have discussed this before, but if you take a Lie category, limonoid without boundary.
Yeah.
Yeah, I think this is going to be better.
You have a limonoid without boundary.
Yeah.
So we have discussed this before. Have you found out the answer? Is it necessarily parallelizable? So does it have trivial tangent bundle?
No, this answer is still open. I mean, this question is still open. I have not found a counterexample, and it might be the case that finding a counterexample of a parallelizable limonoid is somewhat involved. So you for the audience, like you already know any Lie group has a trivial tangent bundle, right? Because of left invariant vector fields, yada yada. And now the question is whether the same holds for Lie monoids, right? Do Lie monoids have a trivial tangent bundle? And it's not easy to answer this question at all. There were some ideas that came from Jure when we were talking about this, but I did not solve that question, no.
But so is this the case even for one object things like the Lie group and the Lie monoid? I mean, so even the classical question is not.
Even the one question, one object. Yeah, no, for many objects, like that's there are counterexamples. Like the algebroids are not going to be trivial, and the tangent bundles of the categories or groupoids are not necessarily trivial. Yeah, but the question is whether this holds for monoids. Like it's just a one object question. So if you come up with any ideas on how to tackle this particular question, let me know. I'd be really interested.
So this is something that Peter might know, because these Lie monoids are generalizations or concrete examples of H spaces. So I wonder if Peter knows some H space which is a smooth manifold but not parallelizable without trivial tangent bundle. Some easy example. I'm not so experienced in H spaces, but perhaps if you have an H space which is a manifold, that could give you some clue towards this question.
So you want an H space which is not an H group.
Yes. So,
Yeah.
but and H space which is a manifold but without trivial tangent bundle, with non-trivial tangent bundle. So all the H spaces that are manifolds, I guess that I know are
So
Lie groups, and this is what Jean has.
was it S7 is probably the first candidate that comes in mind. I mean, the 7-dimensional sphere.
Mm-hmm. Yes, but doesn't S7 have trivial tangent bundle?
Yeah, S7 does.
Okay, so that's a non-example.
That's a non-example.
Yeah, but this is the first
Yeah.
example that I think it,
No,
which is not a group.
I've tried coming up with examples of structures of Lie monoids on S2, which is inherently non-parallelizable, right? And because there's a kind of a natural candidate, you just take the stereographic projection, right, and adjoin the point at infinity and make it like an absorbing element, like a zero or something like that, right? For either addition on this on the complex plane or for the multiplication. And in both cases, I ended up proving that this does not yield the Lie monoid structure, that the operation is not even going to be continuous. Yeah, so that was kind of a non-example as well. So it seems like a very simple question, but I guess the main issue of this thing, of this question, is that because left and right translations are merely smooth and not diffeomorphisms, their differentials of left multiplications at identity or whatever, these are not going to be isomorphisms. So because these guys in general give us the parallelization, right? And because these guys are not isomorphisms, like there's a possibility that this won't hold anymore. that the tangent bundle is parallelizable.
Okay, another example, and maybe is this Hilton-Reuter criminal. It's another example of a space which is an H space, which is okay. It's not legal.
Okay, but does it have a smooth structure?
I have no idea. I'm not
Okay.
talking about that.
Okay.
But that's probably known. So.
What did you say it's called?
Okay, so it's easy. You just look at. So that was kind of the first example of this kind. It's called Hilton and Reuter, the two guys that invented it, and it's called criminal because.
It right previous scopes.
Yes.
Hilton Reuter.
Yeah.
Reuter. I'll Google it.
Yeah.
See what's there.
But I mean, my guess would be that it has a trivial
Tangent bundle.
because otherwise, I mean, this would be a very well-known example.
You mean in the theory of Lie monoids?
Yes.
No, but the issue is that, like, even though Lie groupoids and Lie groups are really well researched, Lie categories gain negligible attention, and that holds for Lie monoids as well. So, so I don't think this is like I haven't encountered any standard literature on Lie monoids up to this point, or Lie categories, just Lie groupoids and Lie groups. So basically, it seems like nobody's asked these sorts of questions. Like there are maybe a few questions on math overflow regarding how to even define a Lie monoid, if that's even sensible, and it is. But yeah, there's not a lot of research going on in this direction.
So I guess Jure had another question.
Jure?
Yeah. Okay. So. The second question is regarding when left and right algebroids are not isomorphic. These examples that you gave were, if I believe correctly, all such that the reason was trivial because there was difference in dimensions between the algebroid of Corbupoid and yeah. So do you have some counterexample where these two are not isomorphic,
No,
the same dimension?
No, I don't have a counterexample of a Lie category with non-isomorphic left and right algebroids, but like this isomorphism is obviously not canonical anymore, right? So in the case, like if one were to prove the general case that the left and right algebroids of a Lie category are isomorphic, they would have to resort to a certain, deep trickery. So, and this is currently ongoing work with me and Johan Markut. He suggested using sprays of Lie algebroids to prove this thing, that these two are in fact isomorphic. But there is only hope that this proof is going to work for the case when a Lie category has a normal boundary. So, you know, the boundary is going to be a wide subcategory. Yeah, that's ongoing research still. So I think I'll be able to answer your question in a couple of months.
So this paper that you posted on archive, have you sent it to some journal already?
Yes, it's currently under revision for what's it called? The Journal of Non-Commutative Geometry. Yeah.
Okay, thank you.
Welcome. Are there any more questions? Okay, if not, I guess we
Okay, so
conclude.
we'll stop here and so you can send me a title and abstract. I mean, it can be part two, of course, but
Okay.
if you have anything to
Yes,
add.
there are other interesting topics. If the audience is like interested in this, I'd be willing to talk about the ranks of morphisms, which literally addresses this question, and extensions to Lie groupoids and stuff like that.
Maybe about the motivation from the beginning with physics. So that also part of the motivation for why you're researching this?
Yes. So the original motivation comes from the notorious thing from quantum physics, right? You have the wave function collapse. So, and wave function collapse is going to be an irreversible process. So, but then after considering a couple of examples